the first presentation of today by Andrea Alberti, who's a member of the other Institute of Applied Physics, the one in Bonn, in his case. And Andrea has a long history of work related to single atoms and work related to adornox. Andrea is a senior scientist and principal investigator at the Institute of Applied Physics at the University of Bonn. His main interests are few atom quantum systems and digital quantum simulation. And Andrea started out his early career in Pisa, in Italy, of course, where he did his master thesis, and his master thesis also had components taking base in Christoph Salomon's lab at Paris. And he was doing his PhD project then afterwards at the famous institution as well. So he was doing his PhD in Florence at the European Laser Institute in the group of Trino. And after that, he was joining the University of Bonn. At the University of Bonn, he was going through various stages of being promoted from postdoc up to senior scientist and principal investigator. And he's going to tell us about, especially today, I think he's going to tell us about the atoms and their quantum speed limit. And we are looking very much forward to your presentation. Please, Andrea, go ahead.
Gerhard, thank you very much for this very kind introduction, and welcome to everyone. Good morning, evening, and afternoon, depending where you are. It's a great pleasure for me to have this audience, to present some of our recent work we've done in our laboratory in Bonn, in Germany. But before starting, indeed, today is the last day, so I would really like to thank the whole organizer, Luigi, and all of the others for this great series of talks. It became very enjoyable habit every afternoon for me here in Germany to tune in and to listen to very interesting, stimulating talks. I very much appreciate it. So the story I'd like to tell you today about is how fast one can transform quantum states. And this is a quite general question with deep implication for much of what we do in our field of quantum technologies that ranges from quantum simulators to quantum computing, but also quantum metrology. And ultimately, it even informs us about the maximum rate of information processing that one can attain. The way we tackle this question is from, we are experimentalists, so we do experiment and we use as a platform the transformation of matter waves. And we find that this is quite a powerful tool to tackle this question, as it indeed has many levels that we can explore. And to give you just a short anticipation of the kind of physics I want to discuss now, so we consider a system that we can prepare in some clean state, can be the ground state, but also some higher excited state, like the first vibrational level. And then we realize a very fast quench of the Hamiltonian. So we change suddenly the lattice potential position in such a way that we activate the motion of the matter wave. And we have developed tools that are based on fast matter wave interferometry that we use to learn about this coherent evolution. And for the purpose of this talk, so the title of the talk is Pushing Atoms and Their Quantum Speed Limit. So I will be specifically looking for today at the very short time dynamics to understand what constrains their speed of evolution. So the problem has very deep root in physics, dates back to the 17th century, when the first to pose this question in a sharp way was Johann Bernoulli. And back then, it was not unusual for the time to address the entire community with such a kind of challenge. I just read it now. Perhaps many of you have already encountered this. Johann Bernoulli, addressed the most brilliant mathematicians in the world. Nothing is more attractive to intelligent people than an honest, challenging problem, whose possible solution will bestow fame and remain as a lasting monument. And to this challenge participated none less than Newton, the big rival of Johann Bernoulli, his brother Jacob Bernoulli, Leibniz, Del Hospital, and others with successful solution. So ultimately the solution was found, and what is the problem? First of all, so Bernoulli asked the question, what is the optimal way to drive a body from point A to point B, subject only to the action of gravity? Naively, one could use a straight line. However, that was already Galileo Galilei realized before Johann Bernoulli, the straight line might not be the most optimal approach. Indeed, it's convenient to gain some speed through a steep curve, even if then we have to pay the price of a longer path. However, this also is not the optimal solution. Eventually that was found and is the cycloid, and we see the little animation reveals clearly with the winner. So we have the loser is the straight line, then we have the runner-up, the steep curve, and the real winner is the cycloid. That is in the quantum world. And then the classical world, when it comes to the quantum world, it comes to mind, I think almost immediately, the Heisenberg uncertainty principle. That is something that informs us about the relation between time and energy uncertainty. The Heisenberg uncertainty principle is something, it's all fine, and especially when it comes about the position on the momentum that are operators, and we understand, and this is perfectly fine to write like this, and we know this the uncertainty of these operators. We understand what that means. In the case of the uncertainty relation expressed for time and energy, this is something a little bit more blurry, and in fact, it's been subject to great debate back then by the founding fathers of quantum mechanics, for the reason that time is not exactly an operator. So then out of this controversy, Mandelstam and Tam came with a solution. It's an operative solution, and they consider the problem of studying the evolution of the wave function, so projected on the initial time 0. And they consider this two-time state overlap, and they look how the trajectory of this evolves in time. And we know from the Heisenberg uncertainty relation, as I said, it's something a little bit blurry, and I'll leave it not specified exactly. So if you see my mouse, so this is, I just leave it like it is. And it's of the order of this fraction, and it can be a straight line, but indeed that is a bit too naive. An optimal approach can't be a straight line, especially because we know that from the quantum Zeno literature, that for a very short time, this two-time overlap function must be quadratic with the time, and the quadratic coefficient depends on the energy uncertainty. So it must be more of the form of a parabolic trajectory, but might it be that the other terms over there could be used to make this dynamics a notch faster? Can we make it even faster? And well, the answer is no, this is not possible. And this was found by Mandelstam and Tam. They found a bound that this applies to all unitary system that constrains this overlap function to be outside of the H region. It turns out also that this bound is saturated for two-level system. So the very simple two-level system is capable of saturating the bound. So we can say this is the fastest dynamics one can find. And this is when the system performs Rabi oscillation. But this also is a bit too simple case and well understood, and we're not interested in that. And we want to consider how these bounds apply, how this bound apply to multiple level system as matter waves. Beyond that, there is a second bound that in fact resembles more the kind of the straight line we had at the beginning. We see at the for a very short time, the second bound does not apply. So the dynamics is constrained by the Mandelstam-Tam bound, but there is the possibility for a longer time that then there is a crossover and the dynamics is constrained by the Margolus-Levitin bound, a bound that remarkably has been found about more than 50 years after the original one by Mandelstam and Tam. And so thanks to Mandelstam and Tam, now we can exactly say with with precision and with rigor what we mean by orthogonalization time. This expression takes a very clear and well-defined value. And so we set out here to establish experiments capable of, first of all, measuring this quantity, the two-time state overlap, something that by itself I find as an experimentalist quite intriguing, the possibility of having a direct measurement of this quantity. Of course, one could think of having some tomography and post-processing and reconstructing this quantity, but we would like to have a way to directly see this in an experiment, and we need to find a way to project the wave function on itself, but at the time t equals 0, which is at first not obvious how that works. But there is a trick. And the trick is presented here in the first part of my talk, so that we posted now recently on the archive this work. And the second part of the talk will show how then there is a new twist, how the story evolves further when we look at transforming matter waves between distant states. So, but for starting, this is a collaboration that took place with the group of Yoav Sagi at Technion, which I have much enjoyed. And especially I so much enjoyed to have here in our group Gad Ness, a student of Yoav that spent a period of time with us and working together with Manolo Rivera Lam, the other student that carried out the measurement. So the setup, in essence, it's an optical lattice, so it's an optical standing wave, deep where atoms are trapped. We use cesium atoms, and what you see here is the fluorescence image of two cesium atoms that are highly resolved through our objective lens that we have developed in-house with, I would say, a state-of-the-art numerical aperture. And so this is a two-dimensional lattice, but for the physics I'm now going to present, it suffices to think about one-dimensional system. The other thing that is peculiar and particular of our setup is the ability to trap atoms spin dependently. So we can create really independent trap for spin up and spin down. So we choose two internal states, hyperfine states, to define our spin of the atom. And now, how do we do this measurement of the two-time state overlap? So we use what we call fast matter wave interferometry. We start from an atom preparing a clean state that can be an eigenstate, that is an eigenstate of the lattice potential. Here in the illustration, the ground state, before I showed you a movie for the first excited state. And then we add a second lattice potential. In this potential, we can control its position with sub-nanometer precision. We can at will define the displacement, and through a very fast Raman pulse of about 50 nanoseconds, we are able to create a superposition of the matter wave of the atom at this point, wave packet in the lower potential and in the potential for spin-up state. At this point, this wave packet start to evolve in time. And so this is how we realize this very fast quench of the system dynamics. And eventually we close, this is an interferometer, and it's a Ramsey interferometer. And we have heard yesterday from Peter Zoller about Ramsey interferometry. And there we see again an application of Ramsey, how this is really useful in AMO physics. So by performing the Ramsey interferometer, we read out a Ramsey fringe. And of particular interest for us is the contrast of the Ramsey fringe. And if you look at the contrast, this is equal to the projection of the wave function, the orbital part of the wave function in spin up with the spin down wave function at time t. But, and here is the trick, so the spin down wave function occupies a steady state, it's a stationary state of the lattice potential. And thus it's essentially the same. So it only picks a phase, and it's the same at time 0. And this eventually was the same as spin up wave function. And there we are. We have a way through the contrast of the Ramsey fringe to directly measure the two-time state overlap. But this is also something more, because actually we are even extracting the phase of the fringe that reveals even more information about the system. So when we create this excitation, we are really creating a superposition of many emotional states. And when we place the atom on top of the potential heel, in that case, we really are occupying states in the continuum. So the two-time state overlap is the sum, is this series, and the sum of terms weighted by the population of the different vibrational states and the peak different phases. And overall, so if we look now at the real and imaginary part, so the contrast would be exactly the absolute value of this. Now here I'm just giving you an illustration of what kind of data we can record with this setup and this trace. And it's, for me, quite remarkable how much information we can extract from this type of traces in time without knowing anything about the potential. So we just do everything like a model agnostic way, and we can retrieve through an analysis of these long traces information about the occupation of the different levels and the energy spectrum. And also some interesting physics that will not be the subject of this talk, because from now on, I want to focus on the short time dynamics here. So we want to look at the short time and to realize how fast this evolution at the onset can be. And there we are resolving this with more points. And here are three representative set of data that we acquire for increasing strength of the excitation. So we are essentially the delta X, if you remember, is this parameter that tells us about the displacement of the wave packet at time 0 from the potential minimum. And as we increase it, we are increasing the energy of the excitation. And what we see first is that the unified bound that in the community, in the literature of quantum speed limit, is understood as the maximum between these two quantities is the Mandelstam bound, and this is the Margolus-Levitin bound. The maximum of this is the unified bound, and well, the unified bound is verified, so we are safe, and this is the first good news. The second point, and more interesting, is that we are observing this crossover between the regime for a short time, where we are dominated by the Mandelstam bound, and for longer time, where it is the Margolus-Levitin bound that constrains the dynamics. However, in certain circumstances, we see that clearly the Margolus-Levitin bound plays no longer an important role. And this is, I will now elucidate more on this as we did further experiments to clarify when this occurs. And if we look at the two bounds, the Mandelstam and the Margolus-Levitin, we see that this is a simple algebra. We get the manifestation of the crossover when this inequality is fulfilled. That translates in having a critical time that is related to the ratio of the energy and the energy uncertainty. And following this algebra, you don't have really to look into it, but to trust me, this condition happens when the energy uncertainty is bigger than the mean energy. And we did experiments under several different circumstances and conditions to look when this occurs in the experiment. And here's the region that we call it. So in this diagram, we call it the Margolus-Levitin regime when the crossover occurs. And these are the data recorded when we create at the beginning. We start from n equals 0, n equal 1, and n equal 2 vibrational excitation. And we see that for most of the points, essentially the dynamics is constrained by the Mandelstam bound. However, for this series of data for n equals 0, and especially for very low excitation, so must be said here on the axis, what we have is the inverse of the Margolus-Levitin orthogonalization time, that is essentially a representation of the mean energy. And on the y-axis, we have the inverse of the Mandelstam orthogonalization time, that is an expression of the energy uncertainty. So we see that in this little corner here, indeed, we observe the manifestation of this crossover. And this occurs when there are very few excitation. And there is we were a little bit puzzled. Then we found there is a very simple solution to this to understand the physics involved here. If we think about the qubit, is as simple as the qubit. When you have a very small excitation, it's mostly in the ground state and a little bit in the excited state. And then the qubit applies. And in the qubit case, we are always in the Margolus-Levitin regime when the spin down state is more occupied than spin up state. And we saturate the bound of Mandelstam-Tamm when we create an equal superposition of spin down and spin up. And this corresponds to the case of a clean Rabi oscillation. So we have seen that these two bounds are verified. And we also did more investigation about deviation from the bounds. And we rely on some geometrical approach based on the Fubini study metric. And it's something that I'll be happy to tell you more about if there is any question. But now, in the interest of time, this is the last remark that for larger energy or larger excitation, like Poissonian statistics for a coherent state, then we clearly get in the Mandelstam-Tamm regime. And this is understood because as we increase the energy, so the energy uncertainty gets smaller than the mean energy. However, we also see that our data do not fit to the simple semi-classical evolution of a coherent state as we have important anharmonicity. So now, changing subject, I want to present an evolution of the story. So it seems that so far so good, and these two bounds form a unified.
10 minutes to go, Andrea.
Yeah, thank you, Gerard. So this gives a unified bound and describes the dynamics of the system, but there is now here a twist. And I want to present a case where the Mandelstam-Tamm bound spectacularly failed to give useful information on the time scale of the dynamics. And this is the case when we transport, transform wave packets between distant states. So these are our two heroes of the story, Mandelstam and Tamm. This is the bound expressed in a different way, but essentially gives us a minimal bound on a lower bound on the shortest time, a lower bound on the time of the fastest process, the Quantum Brachistochrone. Brachistochrone comes from Greek, brachistos, shortest, chronos, time. And if we consider the system of a two-level system where we want to transport the wave packet between states that are adjacent to each other, then in this case, it's all fine. We can use local coupling operator to realize this transformation. And the Mandelstam-Tamm indeed gives us useful information on the dynamics. However, if now we consider a transformation between distant states, then in this case, things fail, because we cannot use anymore, so we cannot reduce anymore the system to a two-level system. We must necessarily consider the intermediate state, as there is no way to transport the matter wave from point A to point B without passing through the intermediate states. So in this case, we see that the overlap between the two states vanishes. This overlap gets 0, which means that the arccosine gets pi over 2. And it would not be hard to show that the energy uncertainty in this process for an optimal transport from point A to point B must increase at least as the square root of the distance. Meaning that this term here on the right-hand side, this, as the distance increases, this tends to 0, which shows that essentially the bound is useless. As in fact is telling us that the shortest time to realize this process, it must be bigger than 0 when we go in the limit of very long distances. And clearly what we expect intuitively is a bound that must at least increase with distance, and instead this one does exactly the opposite. It goes to 0, it vanishes. So there we did an experiment, and also we elaborated a theory to correct for this problem on this Mandelstam-Tamm bound and to take into account the intermediate state that are missing from the bound. So we consider as a basic setting the transport of a wave packet prepared originally in the ground state to an adjacent site. And what we want to achieve is not this. In this case here, atoms are quite excited. We want rather to have atoms back in the ground state. And so this defines the fidelity of our process. And we have developed experimental procedure how to directly measure the probability of atoms populating the motional ground state. The way we realize the transport is through setup that we call it, I will not go into detail in the interest of time, but we call it Polarization Synthesizer. And I would argue that it is the best polarization synthesizer for states of polarization of light that you could find around, as this allows us to dial any arbitrary polarization here. And by doing so, we can control the position of the two optical standing waves, trapping atoms in spin down and spin up arbitrarily. And this is the tool that we use for the transport of atoms, let's say in spin up. So we also do Mach-Zehnder type of interferometry, but now considering just the transport of a single spin state, we could do it with a linear type of approach, but this would be too naive and indeed would create quite a few excitations at the start as we kick the motion, and then when we stop it. So what we indeed need here is a form of control, just like when the waiter wants to reach a distant table with a tray of champagne glasses. What it does, it accelerates, but before accelerating, it tilts a little bit the tray to counteract for inertial forces. So that's the kind of things we also do here. We use quantum optimal control theory to develop optimal strategy, how to transport atoms and to make a connection. If you attended, if you remember the talk of Wolfgang Klitzing last week, so I presented shortcut adiabaticity solution for the problem of transport with a pendulum, and also gave a very nice illustration how that works. And that's the kind of starting place for this optimization. But then because our system is not like a pendulum or a harmonic pendulum, we have important anharmonicity. So we need to take this into account. And then we come up with solutions that are quite wiggling to compensate for kind of fluctuation of the wave function. And this is the results.
4 minutes to go.
Yes. These are the experimental results. We see that when for sufficiently long time, essentially our fidelity is consistent with 1. So we can accomplish this transformation and landing with the atoms back in the motional ground state. However, as the time gets shorter and shorter and so on, then we reach a wall, and where this optimization is no longer possible. And we call this a transition from a quantum controllable regime to a quantum non-controllable regime. And I think this is the first time that this transition has been so sharply resolved. The dashed line is the case when we have exactly 0 temperature. So we argue that we are essentially realizing here the transformation at the quantum brachistochrone, so in the shortest possible time. And for comparison, for reference, this is the Mandelstam time, and we see that this time scale has nothing to do with what we observe in the experiment. Is not really useful, even for the problem of transporting atoms over a single lattice side. And instead, we have developed if you want, a way around this problem, accounting for the intermediate state that the atom must go through, because it cannot be simply transported from point A to point B. And in doing that, we come up with better description of the minimal time for the quantum brachistochrone process. And if we compare this data to the case of the naive approach, we have a linear transport ramp. We clearly see that does significantly better, even when we would try to exploit one of this revival of the wave function back in the ground state. So if we had a perfect harmonic oscillator, then we would expect a perfect revival. But obviously, in our case, this is not the case. So quantum control here, it indeed plays an important role. And now the last maybe maybe 1.5 minutes, just flash a couple of results to give you an outlook of the things we want to do moving forward. And so we are working now on realizing the simplest type of quantum circuits one can think of with 2 atoms. And we have in mind we have a proposal for this, how to reveal quantum statistics by exchanging distant atoms. And we want to create a series of operations in our 2-dimensional lattice where atoms are either following this path. These are 2 atoms initially prepared at this point here and point there, or following these other trajectories. And in this case, on the right-hand side, the position of the 2 atoms has been exchanged, while on the left-hand side, not. And if we are skilled enough in doing this, then nature will not be able to know what of the 2 paths we have taken. And thus, when then probing the parity of the spin, we expect to observe an interference. And this, the position of the interference fringe would inform us whether we have boson or fermions. And I found this quite fascinating, almost philosophical, because these atoms never came to talk to each other. In principle, they don't know about each other, except that they are indistinguishable. And eventually, by looking at the correlation of their spin, we are learning about their statistics. This then can be generalized to many more atoms. We're working on filling the lattice, as Gerard does beautifully in his experiment. We'd like to do something in this way, and then taking advantage of our spin-dependent lattice in 2 dimensions. We are planning to realize arbitrary quantum circuits, and we have clear ideas how this can be realized, like in the fashion of photonics, but with a new twist. So we can realize or we're working on realizing any arbitrary unitary for indistinguishable particles, and with a new twist that here we have also interaction at hand. And in the past, we have worked on the Angum-Mandel interference, something that has also been beautifully demonstrated in the experiment of Cindy Regal and Markus Greiner. And finish with, this is just an advertising of today. We posted a paper on the archive. It's for the experimentalists who are interested how to image trap potentials. And you probably know how sometimes important it is to align multiple beams with micrometer precision, or if you have painted potentials, how important it is to know what potential you have. And here we have a technique that uses Ramsey interferometry to reconstruct a map of the potential landscape precisely with micrometer precision. So I conclude. So we tested the unified bound. We found that in a multi-level system, we've observed for the first time these 2 bounds, and they are crossover. And we show that they are providing useful constraints on the quantum dynamics for a time-independent system. However, for time-dependent systems, especially where the final state cannot be reached by a local coupling operation, we have seen quite spectacular failure of the Mandelstam time bound to provide useful information. And we use optimal quantum control to establish the Quantum Brachistochrone process. And so we've seen this transition to quantum non-controllable regime. And the final message is that the more energy levels you can control, the fastest you can go. And this I finish, thanking all the people listening and acknowledging the group and the people that have worked with me, Manuel Rivera Lam that did the experiment, and Gautam Ramola for the Ramsey imaging of dipole traps. I just now flash the slide, and our theoretical collaborator, and Dieter Mescheder, with whom I'm sharing the experiments.
So thank you very much from us for this presentation. And I would like to start the discussion by calling the question and answer box. And we have a question by Andreas Osterloh. And he says, quantum non-controllable, some of the points seem to be at a fidelity larger than 1.
Yeah, so thank you. Indeed, that was a good observation. So we see that for a very short time, so this is now referring to larger than 1, I don't see it, but no, so it probably refers to to this increase of fidelity here, I assume, because the quantum uncontrollable part will be in this region here, and it's clearly not larger than 1. But we see a revival of the fidelity. And this is something interesting. And the reason why we see this is that because we go so fast that there is a probability for atoms to remain in the motional ground state of the original site. So these are atoms that are not transported at all. And at the beginning we were puzzled, but then we did a simulation and we could understand what was happening. These are atoms that are essentially tunneling through the potential barrier and landing back in the motional ground state, but of the wrong site. And our technique, this is kind of an artifact, if you want, of the measurement, does not here discriminate between different lattice sites. So we're not looking at position resolved. This could be done, would involve more statistics of identify single atoms.
No, thank you. But I was talking about higher times, at time beyond 8, 9, 10, 11. There are several dots on top of.
Yeah, that's right. We have some dots. So this is due to the fact that it has been renormalized. So it's related to the technique that we use to measure this fidelity. And so by taking the ratio, sometimes we obtain points above 1.
Okay.
So if I may add, this is just the statistics of a real experiment. You can get points which are outside of what you expect. So this is what you see all the time in different measurements.
Yeah, but actually, I would expect the error bars would be bigger then.
This is an ensemble average and has been renormalized. So we have some points that, because of detection noise, can be above 1. And indeed, we're not way far away, the error bars, just because we are 1 RMS away. It's normal to have a few points 1 RMS away. It would be suspicious if all points would be just within 1 RMS on top of the theoretical line. So, 68% of the point need to be, but at least a good portion, or more than 30%, need to be further away.
Thank you.
Okay, do we have other questions or comments to the presentation? Luigi, please go ahead.
Yes, I have many questions, but I think maybe thanks for this very nice talk. I think I enjoyed very much. So very basic. Maybe you can explain a little bit more on. You talk about Ramsey interference that you use to in your experiment. Can you please comment a little bit more on that? What you do exactly in your experiments?
So the experiment is creating a superposition of spin up and spin down states. So we drive this transition very fast. For that, we have installed Raman laser system that allows to drive with Rabi oscillation in the 10 megahertz range. And that's why in a time scale much shorter than the typical time scale of motion of the system, we can prepare the superposition of the atom in the original stationary state and the atom in a higher excited state. So this is a transition, if you want, that does not resolve sideband. It's all the other opposite regime. We just do exactly the opposite. We don't resolve sideband. We put the atom on this further up excited state. We let this evolve. And then we run exactly the same pi/2 pulse by controlling the relative phase. So we control the phase of the second pulse, and this allows us to record a Ramsey fringe. And this is what is standard Ramsey interferometry. Now the fringe will depend. So, this is like a Mach-Zehnder interferometer. If the wave packet will not overlap anymore, regardless of what phases they pick along their way, if then spatially or not, also optically, you can think of recombining optical wave packets. If they do not overlap, then the contrast would be very low. And in fact, the contrast it exactly expresses a measure of the overlap of spin up and spin down, and that's what we use together with the trick that spin down wave function populates one of the eigenstates of the system.
Okay. Yes, I think I follow it now. Yeah. Yes, I have. I don't know. Maybe I can ask you only one question more on.
Go ahead. Go ahead. Just ask.
Okay. Say, I saw that in these bounds that you have, somehow can change. So I think there were situations in which the bounds were in a different, in a certain relative position, and for some other regimes, I think the linear bound that I don't remember how it's called actually goes inside the Mandelstam bound, right? So yeah, this one. This is yeah. So can you please explain how come? So what is the parameter to change in this in the distinguish the three positions?
Yes. Probably you are referring to this curve that you see here.
Yes.
This is a measure curve, but in the sense that, so this, it's the prediction based on Margolus-Levitin bound that you see here. So it's simply plotting this where we have measured the average, so the mean energy. So the mean energy is measured, and then we are plotting this quantity. For the purple curve, it's the other way around. So we are measuring the delta E, the energy uncertainty, and then we are plotting this quantity. And then we are comparing against the 2 time state overlap points that you see here. So the fact that, in fact, that's what we were investigating and were interested originally, that's what triggered this investigation, is to understand when one or the other bound plays an important role. And we find that in situations like this, actually the dynamics is constrained by the Mandelstam bound, and the Margolus-Levitin plays no role, because as you can see, yes, it is fulfilled, you know, but it says that everything needs to be above this line, and obviously it is because the Mandelstam prevails in this case. Okay, so actually the parameter is this delta x, so it's the displacement from the equilibrium position that actually. Absolutely. Okay, so in this. Okay. So when excitations, there are more excitations, then it's one bound. You have one bound. You have less excitation. You have the other bound. Absolutely. Okay. I see.